first, we have to get the data moving. Second, we have to label the data intelligently. But third, we have to preserve the relationships between the points of data so that those things can be walked, can be learned by an algorithm. The problem is threefold. First is I can't train an AI without data. The second is that I can't train an AI without meaningful data. The third is that the kind of current excitement around data or AI, which tends to be LLMs or generative AI, is heavily dependent on relationships. Just like a data point in a machine or any data source is not an island, but has relationships with other data sources, manufacturers are not islands. I need the data from my suppliers because that data is a part of my finished good. It's a part of what I need to understand about my operation. If there is a quality problem, I need to know the source of the quality problem.
Jonathan, welcome to the show. Thank you so much for joining us today. Such a great pleasure to have you on. So maybe to kick things off here, could you please introduce yourself to the audience and tell us more about CESMII?
Yeah, you bet. Thanks so much for having me on. This is great. I'm Jonatha Wise. I'm the Chief Technology Architect at CESMII. CESMII stands for the Clean Energy Smart Manufacturing Innovation Institute, and that's why we go by CESMII or just the Smart Manufacturing Institute. We're one of, I think, 17 or 18 now Manufacturing USA institutes. So all of our purview is to kind of improve the state of US manufacturing. Each institute has a different focus. There's one focused on remanufacturing, one focused on cybersecurity, one focused on additive. Our focus is in the name, clean energy and smart manufacturing. In order to accomplish that in the US, we need to work globally. So there are similar institutes and organizations in Europe and in Japan that we work with regularly. But we are focused on the needs of US manufacturers. And if there are international collaborations, we're doing that with the US in mind, ensuring that we're competitive players in the world stage, but also taking advantage of kind of the best technology innovations here in the US.
Awesome stuff. Looking forward to a great chat and learning more about the work that you're doing at CESMII. So, I mean, like many manufacturers view artificial intelligence as kind of like integral to the creation of their smart factories, and rightly so. However, a lot of manufacturing leaders also have reported that the lack of adequate data foundation is one of the biggest factors that are hampering their AI use cases. In fact, there's a report that I read a few months back where it was reported about 57% of executives reported that the lack of data quality was a big factor that was preventing them from really getting value out of their AI use cases. So the goal of this session really is to kind of like get your perspective on how manufacturers can best modernize their data architecture for AI readiness. Now, as someone who's been deeply involved in advanced manufacturing technologies, how would you describe the current challenges that manufacturers face with their existing data architectures? What are the most significant pain points that need addressing for manufacturers to move towards AI readiness?
Our survey of manufacturers might be a little bit different. We engage with everyone from small to large. It's typically the largest that get interviewed for those kinds of things. So we kind of see the full spectrum from very large with kind of legacy infrastructures that need to be modernized to very small with no information infrastructure. Some automation or light automation or good automation, but minimal instrumentation, no data collection. A number of our projects are the first set of instrumentation being added to the manufacturing environment. So we see kind of everyone at different points in the journey. For the for those earlier in the journey, typically the small to mediums, obviously it's a different set of problems. It's getting that first connectivity, getting the data moving, but they have a bit of advantage in that they get to take advantage of kind of modern understanding of information while they're doing it. So if they do these projects well, even though their data might be minimal, it's modern contextualized data, and so they're better positioned at the end of that first step to kind of take advantage of AI and kind of modern innovations. For the more incumbent players, the ones that kind of have an information architecture that was informed by the Purdue model, often with DMZs between many of the layers, some of the first problems are just getting data flowing or flowing to the right place. So data tends to get filtered by these layers. What was collected was kind of somebody's idea of what should be historized. But if we assume that a historian is an accurate proxy of what's happening in an operation from an information perspective, we're probably limiting the analysis that we can do. So the first problems for folks that are at that point in their journey are kind of the liberation of the data. One of the things about a IoT architecture or IIoT architecture is that we usually skip levels, right? In a disciplined kind of 80s or 90s approach, those levels were there for a reason, and there were good reasons for it. But IoT patterns often subvert that, and they go straight from sensor to cloud or straight from sensor to a broker. That broker may be in the cloud. And so sometimes we have readier access to data that obviously carries its own pitfalls and dangers. But again, that makes it easier for an information project, a machine learning project, when you can more readily get access to the data. On the other hand, if you're a legacy player, you probably have more of it. So your second problem, once you kind of get the data moving through the layers, you punch the appropriate holes, you expand what you're collecting and maybe move it into a data lake, is to make sense of it. Often the labels for our data are derived from the data source. So if the data source is a PLC, it's the tag name is the label. And that tag name may or may not have been constructed with semantic meaning embedded in it. Some good PLC programmers have a naming convention that has some implicit context in the name. Often it's just something like temperature or D0 or DI underscore something. So just moving all of that data to a lake, just liberating lots of things called temperature, is not a good corpus for an AI project. It's a data swamp. It's a mess that we have to clean up along the way.
Okay, so maybe kind of like to get a sense of the impact of these challenges, kind of like when you talk about the lack of liberation of data, or kind of like having this data live in silos, as it were.
Yeah.
How do you see these challenges affecting the implementation of AI? Like, why is that such a big deal?
Well, the problem is threefold. First is I can't train an AI without data. The second is that I can't train an AI without meaningful data. The third is that the kind of current excitement around data or AI, which tends to be LLMs or generative AI, is heavily dependent on relationships. An LLM trains on the relationships and strength of relationships between words, or more accurately, tokens. These tokens are frequently related to each other. And so when an LLM is constructing a sentence, it's constructing that sentence out of a corpus of relationships between tokens and other tokens. Just moving manufacturing data, just labeling manufacturing data, but not preserving those relationships between the data points, means that we don't have a useful training corpus for the kind of AI that everybody's excited about right now. first, we have to get the data moving. Second, we have to label the data intelligently. But third, we have to preserve the relationships between the points of data so that those things can be walked, can be learned by an algorithm.
Awesome. So maybe now to kind of like turn to the focus on the solution to these challenges. So I found also in my experience that kind of like this really requires a well thought out kind of like architecture or data architecture for you to be able to kind of like leverage data for advanced analytics use cases and AI. So maybe to kind of like paint a picture for our audience here, could you give us a description of what do you see as being the key components of this modern data architecture that would support AI readiness? So either it's from like legacy equipment, or if kind of like for small to medium enterprises that you spoke about, as they're kind of like starting out from the ground up, how should they think about what are the key components that they need to have in their data architectures?
Yeah, to a fault, and CESMII's sponsored some 50 projects. We always have them start building up, whether it's a new data source, their first instrumentation, or exploiting an existing data source in a legacy architecture. There are 3 steps everyone should go through. So the first is the connectivity and the adaptation to the data. Most manufacturing environments are what we would call heterogeneous, meaning it's a mix of data sources. And sometimes there are like data sources with unlike methods of communication. I'd say many times. I have 2 machines that do similar things, and I would love to be able to train a machine learning algorithm to predict something on one machine, and then take that prediction and be able to run that trained model against a similar machine that does similar things. But the first problem occurs if those 2 machines speak 2 different languages. So we could talk about that being a protocol problem, but there isn't actually value in the connectivity to the machine. It's a necessary step. But just talking raw to 2 different machines is meaningless unless I can translate them into a common language. You might call it a unified namespace if you'd like. But how do I ensure that the 2 like machines are emitting like data? That's kind of problem number 1, is can I translate data sources to a common namespace? Also in the namespace concept, and I think maybe some of the more mature implementations include this, is the notion that the points of data within the machine should not be a flat list. The machine in operation has relationships in the data that I can express with structure. So if I do that with a JSON payload, it looks like a nested JSON payload. It implies relationship. Those are hierarchical relationships. This point of data is composed of these points of data, or this object is made up of these properties. And that's a really good start, is not losing those relationships. Those kinds of like nested relationships facilitate like roll-ups and aggregation. They also facilitate good programming principles like composition. So this machine is made up of subpoints of data, and some of those compositions may exist in other machines. So that's a really good first step that we try to encourage our projects to think through, is not just what are the points of the data in this machine, but are there implicit or explicit relationships in the data that you don't want to lose? But what you can really begin to think about there, and it bleeds into kind of step 3, is the fact that relationships between data are not strictly hierarchical. A point of data may own or be hierarchically related to another point of data, but it may also be orthogonally, non-hierarchically related to another point of data. There are interactions in a machine that I can't necessarily capture in a nested structure. Things like energy consumption may be related to the machine's speed or the machine's quality, but it's not necessarily an ownership relationship where the quality of the machine is owned by the energy output of the machine. So I need a mechanism that allows me to understand the context of a given machine and the interrelationships of its data. And it's important to begin to introduce this concept, whether I exploit it at the individual data source level or not, because I need to zoom out and I need to understand that asset, that data source, in relationship to other data sources in my operation. Easy to understand hierarchical one is that one machine's output feeds the input of another machine. That can be expressed fairly linearly. Often we organize in like an ISA 95 structure, which is hierarchical in nature. But that machine also has these orthogonal, like shooting out non-hierarchically relationships. That machine has an orthogonal relationship to an operator. That machine has an orthogonal relationship to a material supplier. It has an orthogonal relationship to the ambient environmental conditions. Things that aren't part of the machine, but are at points of time related to the machine, are part of the context of the machine, or more broadly, the data source. One of the kind of more important insights that some of our mature projects, mature manufacturer projects are exploring is the relationship between the machine as a data source and the job as a data source. The job is a structure that can be expressed in like a JSON payload, but it has an interaction with the machine such that the limits of the machine, the operational settings of the machine, are different than maybe its physical boundaries based on what job it's performing, based on what it is it's producing. So I have to build up from normalizing the data, standardizing a namespace, if you will, but then expanding my thinking beyond the namespace of the data source to the full graph of relationships, the context that the data source exists in at a point in time. Does that make any sense?
Yeah, absolutely. So maybe just to kind of like linger on that a bit to get a deeper sense of it. So one of the big things that you sort of like advocate for at CESMII is this importance of standardizing on these data models that you sort of like spoke about. Could you kind of like first of all talk to us about why is it important for those definitions to be standards across different vendors and so on?
And just like a data point in a machine or any data source is not an island but has relationships with other data sources, manufacturers are not islands. They exist in an ecosystem. When we're working with the automotive final assembly is taking the output of dozens of other manufacturers, the things they produced, and assembling them into the car that you buy. And the relationship with that final assembly and its suppliers cannot just be parts. It has to be data. I need the data from my suppliers because that data is a part of my finished good. It's a part of what I need to understand about my operation. If there is a quality problem, I need to know the source of the quality problem. If there is a recall in the future, I need to be able to go back and find out all of the parts that are in that car. So let me say it in a positive way. I think the unified namespace exercise is a really good one. It's a really important one because it gets individual manufacturers thinking about consistency and organization of their data. The next step, though, is for those individual teams or individual manufacturers to understand that they will need to interoperate that data with other people in their ecosystem at some point. So if the unification stops internally, if it's just my unified namespace and it's different than your unified namespace, then when we go to share data with each other, we have another adaptation problem. We're all the way back to these data sources are saying similar things in a different way, and somebody needs to translate them for each other. We have to drive consistency across US manufacturing, but across global manufacturing, because no manufacturer is an island. The unification can't stop internally. It's got to be at least aware of other international unification efforts.
Okay, so we talk about standardization of type definitions for things like asset. Does that the standardization also include, you mentioned structures like, say, job related information? Does it kind of like also have to be standardized as well? Is it only for like physical assets?
Yeah, it's across all data. I think every one of our manufacturers in every one of our projects would say, this data is mine. I don't intend to ever share it, right? So the bar is maybe different for that than data that the person I'm selling my parts to wants access to. If they want that data, then standards must be considered. US car is the big three US automotives for GM and Stellantis. And they did this unification exercise for machine event data in a standard that they created for themselves called US Car SAE 53. And SAE 53 is a factory information system event block that they can all standardize on. What's really cool about following like good IT software development patterns for these standards is anyone may specialize, anyone may extend or derive from. The standard is the common core that you agree to interoperate on. You can add to it the things that are private to you that you don't want to share, and that's completely allowed by any of these standards bodies. Take our standard as a common interoperable block and then add things that are private for your environment, and that's okay. For jobs, ISA 95 has a good standard for describing a job emitter and a job receiver. I forget the exact names, but here is how you deliver a job to something that performs the job, and here is how that something gives you information about the job as it's producing. One of our members is working with that standard, and they want extra information delivered to the job performer, the machine, and they want the machine to deliver extra information back to the job emitter. And that's completely allowed. You can extend the standard. Analysis that works against the standard immediately works for anyone who's implemented that standard. We dream about this future where there are off-the-shelf apps that just know how to analyze job throughput. And if you're implementing the standard, you can buy that app. There are other steps required, but an interoperable information standard is the first most important one. There's an organization in Europe called VDMA. The acronym expands in German, so I don't know it, but they're the European Machine Builders Association. And they build machine standards. And one of the key ones that they've released recently is the machine identification standard. They looked across all of the different ways of identifying a machine, harmonized them, and said, this is a building block that any machine can implement that allows you to identify a machine, which is completely missing in our space. Some UNSs include a machine identification, but it's not standards-based, so it can't be discovered by someone else. This simple to deploy building block can be added to an MQTT implementation. It can be added to an OPC UA implementation. It can even be added to like a legacy PLC implementation that allows software to find and identify a machine. That's an incredibly powerful, obvious thing that we haven't had for 30, 40 plus years in our space that every consumer device has since USB came out.
Yeah. I mean, one of the biggest sort of like pushbacks, at least as far as I've kind of like gotten a sense of around the adoption of standards around data modeling is kind of like this idea of saying you have got sort of like a standard that describes a lot more properties than you would say maybe typically need. Yeah. Do you find that to be a problem at all? What's your sense of that?
Not only that, sometimes a lot more properties than you would need. And sometimes the definitions are so abstract that they're not really useful in manufacturing. I think that's a fair critique of many of the the earlier efforts of standardization. Either they're too academic, too abstract, or they have all these properties and nobody knows what they mean and how to implement them. I think the tide is changing towards an approach that is more composition based. So rather than here's this giant monolithic thing, figure out how to adapt and adopt it, to here are some small building blocks that are easy to understand, and you can pick and choose the building blocks that are appropriate for you. Anywhere you've implemented a standard building block, you can exploit it. But anywhere you don't need it, you aren't forced to take it. That's the kind of the beauty of composition is these Lego blocks. You pick the Lego blocks that work for you.
Okay, perfect. Yeah, so we're going to explore a bit later on. You kind of like touched on VDMA, which I believe the basis for their data models is OPC-UA. So I want to kind of like get a sense of why sort of like a CESMII adopted sort of like OPC part 5. But first of all, before we go into that, I want to sort of like also get a much deeper sense of the importance of kind of like having these graphy relationships. You spoke about this idea of that relationships are not only hierarchical, they are orthogonal relationships. So what are the sort of like limitations as far as AI analytics are concerned of having only hierarchical relationships? What does this graphy relationship bring? Like, what does it enable as far as analytics is concerned?
It enables a corpus that's useful for training. Capturing hierarchical relationships is one set of relationships that is useful for training. So a machine learning algorithm can learn that when machine A goes down, machine B is impacted because there is either an explicit or implicit, like within the data, there is a walkable relationship or a discoverable relationship between those two things. A much more implicit relationship, if it's even in the data at all, would be the relationship between a machine and an operator. So this machine goes down more often when Joe is operating it than when Bob is operating it. A machine learning algorithm, given enough data, could probably find those relationships. But if I explicitly express that during a period of time, a shift, a time window, Bob was on, and during another period of time, there's an explicit machine relationship to Joe, then I have two different chunks of data that I can easily compare and contrast, and I being a machine learning algorithm. So we want to simplify the discovery of these relationships by stating them explicitly, by having them available to programmatically discover during training so that the machine learning algorithm isn't left like shooting in the dark trying to find these relationships. And operator is one, material supplier is another, energy source, ambient environment, like you name it, there's these other orthogonal relationships that we should express explicitly so that we can skip that part of the training and get faster to value.
Awesome stuff. So, I mean, you have touched on the unified namespace, kind of like the concept of the unified namespace. So I would like to get your perspective on, as you kind of like look at the bigger architecture, what do you see as being the role of the unified namespace within that smart manufacturing data architecture? Where do you think it fits in, and what are the functionality that it is best suited for?
Kind of your information architecture has interactions with your IT architecture. So unified namespace, as proposed as a concept, is deeply integrated into an architecture that uses MQTT as a protocol, has one or more brokers as effectively data concentrators and access points, hydrates an information model from those brokers into something like Ignition, or at a higher level, into something like SiteWise. So UNS in those cases is more than just a conceptual exercise, making sense of the data. It's a thread that runs all the way through it. In other IT architectures, where maybe there are different pieces at play, Unified Namespace is more of a conceptual exercise of forcing the team to understand their data, to internally standardize their data, to hopefully look beyond their four walls and understand what the rest of the world is doing and see if there are standards that they should apply to their data. But the actual implementation won't take advantage of Unified Namespace as a thread that runs through it. It's more a data exercise. In both cases, it's useful. In the latter case, you're probably taking advantage of other technologies to enforce structure throughout your stack. So a lot of our projects use software from ThinkIQ. In ThinkIQ, the first place you would unify the namespace is in their type and instance system. Types can be imported from profiles, which are standards or standards-based publications. And it's kind of that middleware layer where we first bring the data into a cohesive structure. The difference really, this is a bit of a misnomer, but a bottoms up versus a tops down application of the namespace. In the bottoms up, I want to get as close to the data source as possible where I enforce the structure, and I want it to flow all the way throughout. In the tops down, it's more like these are the standards that I am adapting to, and I'm going to build an infrastructure that provides the adaptation, the normalization, so that by the time anyone's accessing the data, it has been kind of squeezed into the appropriate shape. I could call both a UNS. The former, the bottoms up, is maybe more true to the true believers concept, and the other is more a philosophical approach. But both are valid and useful exercises.
Oh yeah, absolutely. And I kind of like view it as kind of like this bottom up approach where kind of like really pushing out these events out into like this MQTT platform, MQTT broker platform.
And the event is already structured according to the namespace, right?
Exactly. It's all already high quality data, contextualized, and all of that kind of stuff. But then the next question.
And that's the dream, right? Like we would love all our data sources to be structured, semantically useful, already contextualized. That is the right goal. I applaud the goal. I think the reality is more messy, is that I'm going to have to deal with data sources that I can't force to conform in advance. So I have to have a mechanism to adapt them before they're consumed.
And what sort of like do you think like there's a place for a layer between data sources and the unified namespace that does all of that contextualization in the event that the data source doesn't natively or has no capability of sort of like packaging the information in a way that it is useful?
I would wager that of our 50 some odd projects, 90% are that way. The data source can't be coerced into structure in advance. It has to be organized at kind of the middleware layer. So the short answer is yes, that's an important part of many, many information projects.
Okay, perfect. Now, I was about to say the next step for a lot of conversation that kind of like you have whenever you bring up the unified namespace is to say, I'm getting all of these real-time events, but where is the history? Where do I get my history, right? So first of all, what is kind of like the importance of then having historical data in that mix? Where do you see historical data coming into the picture here?
Related to machine learning and AI, I'm almost always training on historical data. For supervised machine learning, it's easier for a human to identify whether the machine learning algorithm has got it right or wrong against historical data that they understand in advance. If I'm training against streaming data, I, as a human, may not fully understand what's streaming through. So it's difficult to know if the machine learning algorithm is learning accurately. So from the perspective of AI, history is critical. From the perspective of many other forms of analysis, I also need history. If I want to see a trend line, the history is either, from a live data source when I started watching the trend, or it's the ability to load that data from storage and paint the trend line so that I can see the trajectory. History is critical. What I would maybe posit is that historians in the traditional sense have maybe been commoditized. I should tread carefully here. A traditional historian is today one valid way of storing history. Buying, infrastructure level historian, absolutely, that's a way to store history. It's maybe not the only way anymore to store history. I might want to load history from my data lake. I might want to load a shorter range of history from an in-memory or local on-disk DB. I'm not necessarily always interested in 10 years worth of historized data. I am always interested in what history is available and how can it be used for analysis.
That's super interesting. And then is it like also for historical data, is there importance of the data model with which the historian or historical database holds that information? Is that of importance as well?
Yeah, still treading carefully, not trying to poo-poo historians, but as a general rule, most historians are historizing key value pairs, the tag name and a sample, the tag name and a sample over and over again. Some of the more advanced historians have another layer that they can add to it, like Pi's asset framework, that can provide structure, that can contextualize those tags, and then can retrieve the data, the historical data using that structure. So that's a really powerful combination. What I'm questioning the value of in 2024 is just raw storing or even interpolating key value pairs. I want the structured data. I want the contextualized data, or at least I want to be able to query the history using the contextual key rather than the raw key from the data source.
Awesome. That makes a lot of sense. Okay, so now I want us to turn our focus on your role and vision as CESMII. I mean, how are you helping manufacturers sort of like, I mean, what we've just described is kind of like somewhat a complex sort of like thing to think through.
Fair.
So
Yeah.
how are you kind of like helping manufacturers navigate the complexities of data architecture modernization, as it were? Could you share some insights into CESMII's initiatives or frameworks that are designed to support manufacturers?
Yeah, absolutely. There's kind of three legs to the stool, or three areas that we invest in. The first is education and workforce development. So we work with educators to create curriculum and resources to upskill the existing workforce and make sure that the next generation is arriving in manufacturing environments with a bias towards wanting to understand the information and make data-based decisions. So we have a whole arm that is just investing in education, and I would say that's critical. The next is kind of in the area of new innovation. We periodically publish areas of interest. and then request for proposals. So we look for projects where the area of interest varies, but what we're looking for outside of the area of interest is there a manufacturer with a problem, and is there a solution provider that is exploiting these concepts or willing to exploit these concepts to help the manufacturer solve the problem. So these are real world manufacturing problems that have a solution in information or analysis of that information. And we support those teams financially, but also with architectural oversight to help them make sure they're going through these steps of making sense of the data, providing consistent structure of the data, adopting standards where appropriate, and then ensuring that the data is accessible in a modern way that preserves the context. And so that's what my team is mostly involved in doing, is supporting those kinds of projects where we can walk practitioners and manufacturers kind of through this modern journey and reduce the cost or risk by leveraging CESMII financial investment. And then the third area, the third leg of the stool, is that we engage with the manufacturing information ecosystem. So the software vendors and solution providers and system integrators in our space who we feel are on the right track, but could benefit from acceleration or could benefit from support, or maybe there's a knowledge gap that we can help them with, or a connection that we can help them make to, a standards group or a standards effort that might accelerate their efforts. And that occasionally includes financial investment from CESMII, where we really think they're on the right track, but we could pour some fuel on the fire. We can do that as well. So in all of these ways, we're taking the CESMII funds, which are taxpayer funds, and trying to accelerate either education in a manufacturing environment projects or ecosystem technology accelerators to help kind of everyone do better.
Awesome. So one of your sort of like offerings is what is called the CESMII's Smart Manufacturing Innovation Platform. Could you kind of like describe to us what that is?
Yeah, the SMIP, Smart Manufacturing Innovation or Interoperability Platform, that's why we like acronyms, is really two things. So the first was sort of a test bed for these ideas, like a reference architecture, if you will. It's the tech where we interact with the ideas. If a standard is proposed, we want to kick the tires and see if it works, if it's actually applicable and useful for a real world manufacturing environment. If it's maybe too abstract or has too many properties that people don't understand, it's a tool to do that kind of learning on, that we provide to our members as a benefit. And that we are like continually evolving the concepts for. From that, what we look to produce is guidance or specifications that any platform could implement to like bear the badge SMIP. Our vision is that there's lots of platforms that count as SMIPs. But then the other is an actual implementation of these ideas that is kind of the beneficiary of some of those acceleration funds. So one of our members, a company called ThinkIQ, was like, yeah, we're aligned. We believe in this vision and we want to be at the cutting edge of it. So as we explore these ideas, they implement them, and they have a commercial offering. CESMII is not a commercial body, but I think they've benefited from quickly taking the ideas that the membership is exploring and productizing them and then offering them to the market. That's what ThinkIQ does. There's a benefit to them to being CESMII members that they get to take advantage of. But that is something we would call a SMIP. And throughout 2024, we're aiming to see a number of other platforms carry the badge SMIP.
Okay, I see. Maybe just to kind of get us a sense of whether I'm thinking about this correctly or not, is do you also, to some extent, act as a kind of like a bridge between the vendors and the end user, as kind of like you propose this ideal architecture and then have sort of like vendors that will be able to deliver on that architecture? Is that a good assessment?
Yeah, my job is to hold the light of where like we want to go, but then kind of deal with the reality that the vendors aren't all there yet. Many manufacturers are at the beginning of the journey. So what are the pragmatic next steps to help a given team take 1 or 2 or 3 steps forward? So yeah, I often espouse like the end state that I would like to see, but then when we engage with project teams, it's okay, what state are you in now, and how can we help you move a few steps closer towards the goal?
Okay, makes perfect sense. So one of the projects that I really find compelling from CESMII is the smart manufacturing profiles, which kind of like are best off of, as I mentioned earlier, on OPCUA part 5. So first of all, I want to get a sense of why you chose sort of like OPCUA as an information modeling standard to base the manufacturing profiles, and maybe kind of like just give our audience a brief description of what we're talking about here when we talk about smart manufacturing profiles.
Yeah, maybe I'll start there.
Yep.
If I think for most of your audience, kind of UNS would be the starting place. So UNS kind of lives in what a data source emits, and like we said earlier, we want that to be well structured, so that when it hits the broker, it is what we expect. The profile is an external document that articulates that expectation. That's all it is. It is the class definition and what a machine emits, the event the machine emits should adhere to that class or implement that class. It should be an implementation of the class. What MQTT does not have in the specification is an external class definition. Many IT languages and environments have this concept that first I define the class, then I instantiate the class. And if the instantiation does not match the class, often I'll refuse to compile, right? Or if I compile, I'm going to have a runtime error because of this mismatch. The profile is the external class definition. And I can implement it in an MQTT data source. I can implement it in OPCUA. In fact, I have to implement it in OPCUA. But I can really take this external document and implement it anywhere, in C#, in Java, in Python. It is just a class definition. It's an external authoritative document that says this is what the payload should look like. And it's a critical part of object-oriented programming. Any type-safe language will have this concept. As an aside, JavaScript is not a type-safe language. It's a prototypal language, so I don't have classes. I have prototypes that I inherit from, and I can be fully polymorphic, and I can change this object on the fly. And that's very, very powerful right up until I want to interoperate the data, serialize my JSON or my JavaScript object to JSON. Then I start to need things like a JSON schema. And that's what we've seen some of the mature players in the space do. Like HiveMQ has, is a broker, but it also has a JSON schema that I can apply to messages on the broker to ensure that the payload matches. It's just an external document that pre-articulates the namespace, the payload, that everybody can reference. The first part of the question, though, is why we chose OPCUA Part 5. And let me just highlight the Part 5. There's something like 17 parts of kind of the base OPCUA specification, and then there's these companion specifications that largely make up information models. The part that CESMII endorses is Part 5. Many of our projects use the other parts, but we are officially agnostic to how you transmit the data. The part that we have an opinion on is that you should have this external document that defines the class or the payload definition. Part 5 gives us that. Part 5 is just the information modeling part. And it describes two things: it's how to construct these things and the format for those files, which is called a nodeset2 XML. The nodeset2 XML is unencumbered by any licensing. Anybody can read it. Nobody has to pay tribute to OPC UA to use it. Anybody can import these documents. They provide free open source reference for serializing a nodeset2 to C# or to Java. It's literally just an open format that you can use to define an information model. Importantly, it can define component information models, like we were talking about earlier, parts of an information model. But the same language can be used to express an entire information graph. It scales elegantly from the smallest component definition all the way to being a serialization of a UML document that describes an entire enterprise. It's powerful, it's flexible, it's compliant with object-oriented programming environments. It's open and free to use, and you can apply it to whatever stack you want to use for your information project. Obviously, we have opinions on what some of the better stacks are, but our kind of base opinion is you should have a schema, you should have a class definition, and you should express it in an open format that other people are free to import so that they can understand your objects or your event payloads. That's why we chose UA Part 5. It was the only thing that met all of those criteria.
Oh, yeah, absolutely. I mean, I really found also like OPCUA information model. Like I've got a very successful series on OPCUA on YouTube. And the reason why I really started kind of like creating that content is because when my first experience with OPCUA, when I kind of like entered the system integration space, I was just kind of like astonished to find that people were using OPCUA just for data access as if it were kind of like just classic OPC.
Right.
As soon as I discovered the power of the information model behind it, I was like, why isn't like a lot of people paying attention to this? And this is kind of like when I went into this.
Those videos of yours are some of the ones that I use to understand it as well and share with our members. And I think they were some of your earlier videos, but you're absolutely right. Most people understand OPC from like OPC-DA, what's now called classic OPC. It's a protocol, arguably not the best protocol, depending on who you ask. There's strong opinions on that. PubSub solves some of the problems, but it's more verbose. CESMII doesn't mandate the protocol. There are many successful projects using OPCUA as a protocol, but if you stop there, for its pros and cons, if you stop there, you're not really understanding what they were trying to accomplish with UA, the unified architecture part. And each of the parts are building blocks. They're take it or leave it. The part we endorse is Part 5. Have an external definition of your information model that other people can read and import, so that you improve your chances of interoperating in other environments.
Awesome stuff. Okay, so can we talk about the CESMII's Smart Manufacturing Marketplace?
Sure.
Can you kind of like give us a description of what that is?
Yeah, the marketplace is kind of evolving as a concept, and maybe the name is a little misleading since we're not actually capable of performing any transactions. You can't buy anything on the marketplace right now. But in its current state, what we look to do with it is, one, highlight solutions that we think are smart, highlight offerings or project output that are repeatable, that we think people should be aware of and consider using in their information projects. And then the other thing is to link those offerings to profiles. So if a standard information model has been used or extended, just have a human discoverable relationship between those things. So I can see that if I have a CNC machine and I implement a standard for a CNC, these are products that I could use off the shelf. And this kind of like off the shelf, download it from an app store is like a dream in our space. And there's a number of reasons we can't get there. But the first one is a unified namespace for a CNC or a unified namespace for energy optimization. And so that's what we're trying to link there is solutions with namespaces or profiles that you could implement to get access to that solution.
Awesome stuff. So can you kind of like, I mean, just kind of like bring everything together, right? Kind of like what we spoke about as far as the data architecture is concerned. I know you've got a smart manufacturing reference architecture. We're going to provide links on the description of this video to all this material. But could you kind of like give us a brief breakdown of what that reference architecture looks like as recommended by CESMII?
Yeah, kind of the same three things that we've been discussing. So adapt and normalize your data. You're going to have heterogeneous data sources. Some of them you can coerce into being modern, and some of them you can't. So you're going to have to do that rationalization exercise of understanding your data sources, bridging connectivity where necessary, and whether you start from bottoms up or tops down, some adaptation is going to take place. So get a handle on that. And define the namespace or profile that you're going to use for that. The second is don't do that in a vacuum. Look to see what other teams have published, what else is applicable to your industry, what standards exist, what VDMA has done and published that you might be able to take advantage of so that your unified namespace is more globally unified, not just internally unified. The third is graph thinking. So don't just capture hierarchical relationships. Lots of our tools lend themselves to that, and that's great. Less tools lend themselves to capturing these graph relationships, but you should be, within your information project, you should be aware of them, and you should be looking for tools or platforms that let you preserve those relationships as you discover them or as you express them. And then the final piece of a reference architecture, and that might be too generous a term, is more like guidelines. But the final piece that we want to be really prescriptive on in 2024 and 2025 is open and standards-based APIs for getting access to this data, not just the raw data, not just the unified data, not just the graph relationships, and not just the history, but all of these things in a standard API that allows for true application portability. Once we have true application portability, we're going to see a renaissance of cool, repeatable apps, of apparently amazing AI innovation that is just not within reach right now because every information project is a brute force exercise trying to pull this data up and standardize and normalize it and understand it. If we can get past that effort by adopting some standards, by not reinventing the wheel every time, and we can focus the platform providers on common interfaces to all of that data, then we can see real innovation start at kind of the app analysis or AI level. And that future's within our grasp. We just have to make sure we don't shoot ourselves in the foot along the way. And CESMII and others are here to help.
Awesome stuff. So maybe just to kind of like give a sense of a real world application of the kind of like your work at CESMII, could you share, do you have a use case where a manufacturer has successfully modernized their data architecture sort of like following your principles and guidelines?
I appreciate that you sent this question to me in advance because like I said, we have 50 some odd manufacturer projects and probably another dozen kind of platform acceleration projects. And I wasn't sure which one I wanted to highlight. So I'll call out first that if you go to cesmi.org/projects, you'll see a summary, and then you can click on and see detail of some more of these projects. You can also watch on cesmi.org because we will have RFPs in the future where if you're looking for acceleration funds for one of your own projects that matches up with our areas of interest, we'd love to talk to you about accelerating you. But the one that I wanted to highlight in the couple minutes that we have brings in a topic that I think has been in the background of our conversation, but we haven't called it out specifically, is that information projects are technology projects, but they're also culture change projects. So the one I wanted to highlight is a company called NBC, Nutrition Bar Confectioners, who partnered with a provider called GWPO. And they were early in their information journey. So this wasn't a unified namespace effort. This was a first sensors effort, that kind of the first access to data. They have automation, but not instrumentation. And these are some of my favorite projects because they don't carry the legacy, but they're also culturally more challenging projects because the workforce has never had access to this information, and as a result hasn't been empowered to react to information that they don't have. So this was a really cool project because GWPO, largely by telepresence, because this kind of happened in kind of the mid COVID times, helped NBC not through just the exercise of selecting sensors, placing sensors, understanding the data, normalizing the data, moving the data to a surface where operators could understand and react to it, but also through the culture change necessary to become a more information-driven manufacturing process. And it was a success. Candidly, not all projects are a success, but this one was because it was the right balance of all the things we've been talking about from a technology perspective, but also sort of an emotional IQ that was necessary to help a manufacturer through this transformation, and then a leadership and workforce willingness within the manufacturer to adapt their processes and react to this information as it became available. And not just react, but like really understand it and really be able to optimize their production, reduce quality, reduce energy consumption. It was all around a win. There's many more like that. Check out the CESMII projects page.
Awesome stuff. So in conclusion, could you, first of all, just have any last words, something that we may have missed during this session, and maybe as an advice to specifically manufacturing leaders? I mean, as you mentioned, this is kind of like a whole cultural change. It's a skills kind of like conversation. What are the sort of like, what is the advice? Where should they start? How should they kind of like begin that process? And if you've got any last words as well.
Yeah, hard to boil it down to some bullets, but maybe a couple things. At the heart of what we've been talking about really is IT-OT convergence. And when we put those two disciplines in the same room, there's often an impedance mismatch, right? Like sometimes they're saying the same words, but meaning different things. Sometimes their technology evolution is so different that they don't understand each other, but it needs to be done because they have things to teach each other. All of these principles that we've been talking about are things we grew up with in IT software development that can be of benefit to understanding OT technology, to making sense of it, to organizing it. On the other hand, IT software often has this idea of move fast and break things. That was my motto for one of my software teams. You can iterate fast with software. What OT brings to the table is not just an understanding of like a logical flow and how the process works and what's important on the shop floor, but also a discipline around engineering that's really important to bring to the table. When you build a unified namespace, if you build software on top of that and then you change that namespace, you break that software. And if you're using that software to make decisions on the shop floor, it's not just productivity that's at stake. Potentially people's lives or welfare are at stake. So these disciplines need to work together. They have things to offer each other. And that's a worthwhile exercise, even though it can be challenging at times. The second bullet point, I know I'm tight for time, is don't just unify your namespace internally. Think beyond your four walls. Look what the standards bodies are doing. Push the standards bodies, right? Like if this standard's applicable to you, but you can't use it, give them that feedback, or work with a group like CESMII who will advocate for you. If you can't adopt a standard, that's a valid piece of information to share with the standards body. And if it needs to be decomposed, if it needs to be broken into smaller parts to make it adoptable, that's a valid evolution of a standard. But we won't get that evolution if we don't have this kind of feedback cycle where people are thinking beyond their internal unification and starting to think about where they fit in an ecosystem in a global world. And then maybe the third is, obviously, if you're not a part of CESMII, come join CESMII. We're trying to help float all boats, and we will meet you wherever you're at in your journey. Don't fight protocol wars. Don't pick religious battles. Think practically about where you are at your journey and seek out the helpers and guides that can help you on the next steps. We all need to do better. We can do that by helping each other.
Awesome. Jonathan, it's been such a great pleasure having you on this show. Thank you so much for making the time.
Thanks for the fun conversation, for having me on the show.
Awesome.